Okay, everybody, we're in chapter 5 and we're talking more specifically about light as energy. And energy is agitation of objects, molecules, atoms, electrons. In fact, that agitation actually has a quantitative measure to it. It is a property that you can measure that is moving between objects or molecules or atoms or electrons. In order for the matter, the mass of molecules or atoms or electrons, the matter that can be hydrogen or helium or carbon in astronomy, in order for that matter to do work. And when you think about energy and measuring it to do work, you might say, well, what work do we do in astronomy? And here's a great example, just to think about the aurora that was in place just this week. That aurora is doing work of powering the atmosphere with electromagnetic energy. So that's doing electromagnetic work there. And in fact, you might say to yourself, well, when I am hearing about energy and a quantitative property that moves between objects, that sounds a lot like heat. And in fact, energy is heat and energy is light. So light and energy and heat are all one system. Okay, we can refer to it as light, we can refer to it as energy, or we can refer to it as heat. Most of the time in astronomy, we talk about light and energy. And the reason we talk about light and energy is because it's really easy to get confused between heat and temperature. And in astronomy, they're very, very different. And in fact, heat and temperature are different. Heat is that property that moves between objects. Temperature is the unit of measure of that movement. So temperature is a degree, a unit of measure, for the average speed of the atoms in the object. And the average speed of those atoms can go up or down with the temperature. Let's look at that a little bit more. It's as though you're saying that temperature is a low speed in cool and a higher speed in warm. And yes, it is. Temperature is a higher speed in warm. And you can measure that temperature with like a speedometer, right? You can measure that speed by using a thermometer. A thermometer is like a speedometer for molecules. It measures the energy that is in those molecules. And in astronomy, we measure the energy really not by Fahrenheit, and we don't even use Celsius. We use Kelvin in astronomy for a very specific reason. The Kelvin is related directly to the motion of particles in the object. And in fact, when we start at the lowest level of Kelvin, absolute zero, it's saying there is no particle movement in the object at all. There are no electrons moving. There is no particle moving in that object. We cannot see absolute zero on Earth. And we're wondering if we can find absolute zero in space. Maybe you can find it. But we use Kelvin, and absolute zero is no particle movement at all. To give you a reference, when we talk about the freezing point of water in Celsius, it's 0 degrees Celsius. This is a Celsius scale here. 0 degrees Celsius is the freezing point of water, but that frozen water still has plenty of electrons moving in it. And in fact, that frozen water is at 273 degrees Celsius, 273 degrees Kelvin. It's nowhere near absolute zero. The electrons in the ice are still moving. They're just moving very slowly. And in fact, when you think about Celsius, it is always 273 degrees off of Kelvin. So for instance, when you go up to the boiling point in Celsius, the boiling point of water at sea level is 100 degrees Celsius. So you add 273 degrees to it and you get 373 degrees Kelvin. We are going to be talking about Kelvin in astronomy because of its relationship to particle movement. And in terms of that, we talk about particle movement and energy quite a bit. And we talk about the fact that energy moves very, very quickly in short wavelengths, so that in short wavelengths, we have more particle movement, we have more energy. And if you think about that, it is directly related to what you see every day. So these are filaments that are heating up. And as they are heating up, which do you think is hotter? I think that you would say the hottest one is over here. And you know, probably from experience, that white hot is the highest temperature that you can see. That red here is starting to heat up and it's getting brighter and brighter. This orange here is starting to heat up and it's going to white hot heat. What is happening there is you're moving from infrared waves, which are infrared, red waves, and you're moving closer into visual light waves, more energy. And as you gather more of those visible light waves together, all visible light together is white. So that is why the prism that comes in with sunlight, that is white light, breaks out into all colors. In this case, you are adding so much energy into the filament that it is able to reflect all colors as white light. So in this case, we are introducing light and energy and wavelengths together. And the transfer of that energy between objects. So for instance, with this coil, with this heated coil over here, how do you transfer the energy in that coil to the air around it? And how do you transfer the energy from the filament through the vacuum of the light bulb to the glass around it? This transfer of energy is very important in astronomy, and we're going to get to that on the next video.